Hey everybody, this is Kai Wehner from Confluent. Today I want to talk about event streaming platforms and service mesh. I will explain how you can build cloud-native Apache Kafka infrastructures leveraging Kubernetes, Envoy and Istio. Let's begin with the key takeaways for this session. Apache Kafka decouples independent microservices. This includes event streams, but also request response and other communication paradigms. Kubernetes provides a cloud-native infrastructure on top of Apache Kafka. So with this combination, it's really powerful and you can build a scalable, elastic and agile platform for your microservice architecture, both for the server and for the client side. A service mesh helps with security and observability, and that's really at ecosystem or organization scale. So this is totally orthogonal or complementary to Kafka and its ecosystem, and for both server and client side. And I will talk mostly about Envoy and Istio, which are one layer on top of Kafka, then using and building a service mesh. But we will also talk about Linkerd and a few other technologies here. You see, for this topic, there's a big agenda. I will cover different points here, beginning with the motivation, challenges, and requirements for microservices, and then take a look into these technologies like Apache Kafka as streaming platform for microservices, and then how Kubernetes and different service mesh technologies can help with that. So I will really talk in the end about how Kafka and service mesh can be combined and when you should do that and when maybe it doesn't make that much sense. And this is the main goal of this session. So in the end, I will show a few practical examples of how Kafka and ecosystem and Kubernetes and a service mesh can be combined the right way. Let's begin with the motivation, challenges, and requirements of microservices. So the world has changed in the last 10 years, right? So there's many new challenges from business side, like integration with millions of mobile apps of end users, like building infrastructure at scale and elastic with the cloud. And the most important for this topic here is microservices, where you really decouple the different producers and all the different consumers from each other. And that's really where you need a system in the middle like Kafka, which provides the storage and back pressure between the different systems. And then, of course, there's topics about high throughput and many other cutting-edge technologies like machine learning. The key here really is that you need to go with new trends, and for that you need new scale, which means you can also do high scalability or start small and get bigger. You need processing at different speed, often in real time or in near real time. Sometimes still batch is fine, but for many new and innovative use cases, you have to act on data while it is interesting and hot. And also another big requirement is that you need to get more efficient. This means agile development and really decoupling the systems and applications and business services, so that each team or each partner or each department can really work on its own business applications separately from each other. You don't build the one monolith anymore, but many different applications. So if we think about microservices, are they the rescue for this at scale? In an agile way and all these things. So, well, they are, but they are not a free lunch. And that's what many people learned in the last years with the first microservice architectures. So this article here is from 2014, and it explained at that time already that it's really hard to build microservices, especially if you don't have the right tooling and infrastructure for that to help you automating all of these things you have. Because the decoupling and the independence of the systems come with its price for monitoring, for scalability, and any other efforts. So if you think about the key requirements for microservices, then you will find out that one of the most important is that these microservices are decoupled from each other. Producers can produce data and consumers can consume data, but they are really not related to each other. They often don't know each other. Often some consumers can consume in real time while others are in batch, and others use other communication paradigms instead of streaming, like request response or maybe just one-way fire and forget. Though that all has to be decoupled and you need a back pressure in the middle. On the other side, it also has to be flexible. Flexible means that you really can also easily scale up, scale down, change things, do things like A/B testing, and really build new innovative things quickly, and also if needed, throw them away or scale them up if they work. You need operationally transparent microservices. With a microservice architecture, you have many different decoupled applications and a lot of server-side infrastructure. And in the end, you need end-to-end monitoring. Do all the messages from the producers arrive at all the different consumers, or do you lose messages? And how is the IT infrastructure running? And all these kind of things. You need to be aware of the data. That's where things like Kafka come in, right? To process data, to analyze data, to be aware of the message structure, and to really use the data the right way. And finally, you have to be elastic. That's really important, because then if you have a small microservice and are successful with that, you need to scale it up or maybe even deploy it over multiple cloud environments or different regions. So that's a lot of different requirements. And here you see it's not free lunch. You have to do a lot for that. And that's now where we can take a look at different tools and how they can help with that. The first one is Apache Kafka, which is really the de facto standard for microservice architectures in the meantime. I have not seen a single project I can remember in the last 2 or 3 years where Kafka is not chosen as microservice technology in the middle and also for the clients. So let's think about why is that. So Apache Kafka is much more than just a messaging system. Many people know it only from ingestion into Hadoop, for example, or another data lake. However, it's very different from traditional messaging systems like MQ or JMS, where you just have a queue which you fill up and then you get rid of the stuff. With Kafka, you have a distributed commit log, and into that you can send new data, and then it's also stored in the log. So Kafka is not just a pub subsystem, but also stores the messages as long as you want. And with that, you really decouple the different producers and consumers from each other. And that's a huge advantage from Kafka compared to other integration layers or messaging systems. And then you can also natively process the data with Kafka, with tools like Kafka Streams, which is part of Apache Kafka, or with KSQL, for example. So Kafka is much more than just a messaging layer, and that's why it's so often used for microservices, because it really decouples the different systems, and also then it allows high scale and elasticity on the client side, and that's very important characteristics. So as I said, Kafka is coming from the tech companies. They have built it 10 years ago for large scale, often for ingestion into a data lake or into another analytics system. However, today the important thing is it's not just used by tech giants, right? So every bigger company on this planet uses Kafka in the meantime for many different use cases. And one thing to really point out here is that Kafka is not just used for big data projects. Today, I think around 80% of projects I see, and I see around 100 to 150 customers per year, it's really much more about smaller data sets, because customers use more and more transactional data and business applications for Kafka. And that is really things like instant payment applications or fraud detection. And there it's not often about petabyte, but more about smaller data, right? Often even just about 100 messages per second. That's really, Kafka can scale much more, but also with the decoupling of the systems and the high availability and scalability of Kafka. That's the reasons why it's used for these kind of applications. It's up for 27 and built for failure, so it can handle failure under the hood, and still you don't lose any messages, and the producers and consumers still work with that. So here I just want to show you a few different use cases, like people building complete new core applications and infrastructures around Kafka, like a new core banking system or like new other booking information systems. And on the other side, of course, still big data applications, for example, for IoT infrastructures. But the point is really, from the focus of this talk, it's about microservice architectures, which is, as you see here, one point in the middle, to decouple the different applications from each other. That's what Kafka is really great for. And why is it great for? As I mentioned before, in the middle you have this distributed commit log, so it makes the data highly available and highly scalable. But on the other side, it also decouples the producers from the consumers. And that's really huge for microservice architectures, because each business unit wants to use their own technology, their own communication paradigm, and their own business logic, and all decoupled regarding different integration for build pipelines and testing and versioning. It's all decoupled from each other. And that's where Kafka, with its storage in the middle, it's really great to do that. So for one Kafka topic, you spread it out to different partitions. That's how you scale Kafka. I don't want to go into too much detail here. The point is really that Kafka is a highly available system on the server side, while for the client side, you still consume the messages from one commit log in guaranteed order. And the big point also is that while producers just produce data, the consumers are completely decoupled from each other. One consumer might be in real time, the other one might be near real time and uses something like indexing into Elasticsearch, and the third one might be a batch system like Hadoop. And then maybe a half a year later, you add a new microservice with request response style like REST or gRPC, which communicates with Kafka. That's all possible because they're all separated from each other. And then under the hood, Kafka replicates the data and makes it highly available. It also supports things like backwards compatibility and rolling upgrades. Therefore, you cannot upgrade everything at the same time in a microservice architecture. And just because one service is down, all the other services have still to run and be available. And that's what Kafka does under the hood for you. You don't have to care about that. And the other important part about microservice architectures is that, yeah, great, you can decouple systems from each other, but then you also have to make them work with each other and speak with each other the right way. Here's an example of different microservices where a booking service produces a booking with a timestamp. The data format is integer here. And however, if a booking microservice then creates a string here with a different timestamp structure, then all the microservices break. And so on the one side, of course, then you could fix all the microservices, but this does not really work in the real world. And therefore, you have to define APIs as a structure here. And therefore, in microservices, you still need contracts, but in a streaming world like with Kafka, it is about event schemas. That's the API, and that's used for governance and for enforcing that the producers and the consumers speak the same language regarding the message structures. And this is now the benefit of both the things. You decouple the different systems, they're completely independent, but on the other side, they also speak the same language so that they can work with each other. So here's an example with Confluent Schema Registry, which implements this logic for you, so you can just configure schemas, including backward compatibility to have different versions of a schema, and then you have decoupled microservices, but they still speak the same language regarding message structure. Today, the Confluent Schema Registry uses Apache Afro with all of its advantages. But actually right now, while I'm talking, we're also implementing support for protobuf and for JSON schema. So that's also coming soon to have more flexibility regarding the data format under the hood. And with that together, then you can really build domain-driven microservices and decouple the server side, which is the event streaming platform, a Kafka cluster, and maybe the schema registry or some other components like role-based access control, which you would provide and configure here. But then also the different microservices in the client side, which are all decoupled from each other. And this is great because now in microservices, each client can decide what technology to use. The first one might use Kafka Connect as its own availability service for integrate with modern or legacy sources or things like mainframes, ERP systems, Salesforce, Hadoop, Elastic, whatever. The second one, like on the right side, could build its own application, and this could either be a Java developer to build a new payment system, or maybe a data scientist which uses a Python client. And then you can also use legacy technologies, right? So each ETL or ESB tool in the meantime has Kafka connectors to integrate with the Kafka cluster. The great thing, all of these are decoupled and can scale in their own way and be available and process the data in their own way. Some could be real-time, some other could be request response. That's totally fine because all are decoupled from each other. So if we reconsider the key requirements for microservices, remember from the beginning, with Kafka and Confluent platform, the great thing is that you decouple the microservice with Kafka as the central log and storage in the middle. You also get some kind of flexibility because you can already choose different technologies for each microservice. And you are definitely data aware because Kafka is processing and storing and managing data, right? However, you still miss the operational transparency. So you don't really know yet what's going on, and not just in the Kafka infrastructure, but also from the business perspective end to end. And also you're not really that elastic yet, because you can add brokers to Kafka and you can add new clients to a consumer group and it scales, but you have to do a lot of these things manually and script that by yourself, and that's not really easy to monitor and implement by yourself. And therefore, Kubernetes comes to the rescue here. It's really built for cloud-native microservices. So let's understand better how Kafka and Kubernetes work together very well. Kubernetes is more or less the real Kubernetes, the real cloud-native platform these days. So 5 years ago, it was different. You could search for Cloud Foundry, OpenShift, Mesosphere, Kubernetes. They all had some kind of tractions and different features and different technologies under the hood. This completely changed because Kubernetes more or less won this battle due to different reasons. And today, more or less every other major vendor for cloud-native platforms has shifted, and their product strategy is now also Kubernetes. OpenShift started with this very early. That was advantage for them now. And others in the last 1 or 2 years, like Mesosphere, even completely rebranded themselves. Or Cloud Foundry now has a pivotal container infrastructure, which is based only on Kubernetes. And the same for Docker, for example. So the key strategy now is Kubernetes. And with that now, Kubernetes is the right choice for building a cloud-native infrastructure. Cloud-native means that you really do automation. You do DevOps, right? The developers also deploy the services and scale the services and monitor everything. And all of that automated with continuous delivery in a CI/CD pipeline. And with that then, you can leverage things like containers under the hood to build decoupled independent microservices and scale and monitor all of them independent from each other. And that's really big. And now the evolution of Kafka went in the same way, of course, right? So in the meantime, everybody plans to use Kubernetes to deploy it in a cloud native, to deploy Kafka in its ecosystem, like Connect and Streams and so on, in a Kubernetes infrastructure. Because you get the same advantages like for any other microservice. However, there's a problem. Kafka by itself is already hard to operate. It's a distributed system with zookeepers, Kafka brokers, Connect instances, Schema Registry, and other components, and of course the clients. And also Kubernetes itself, it's a distributed system. It uses etcd under the hood. It has also many components to run and operate 24/7. It's not that easy. And then merging both of them, of course, it's even harder, right? To give you some examples of what we have seen from our customers with running Kafka and its ecosystem on Kubernetes. First of all, it's hard in general to translate the traditional architecture to Kubernetes, especially for stateful systems, what Kafka is. For stateless services at the end, it's easier, right? But to handle things like failover or data balancing in Kafka to move partitions, that's really hard. And then also connect all the ecosystems to each other. How to provide access to external services which are running on another Kubernetes cluster, or maybe even in a mobile app, and connect that to the Kubernetes cluster. How to provision and connect the persistent storage options. How to automate security and the certificates. How to do rolling upgrades and to do configuration changes in Kafka. That's all hard stuff you have either to solve by yourself, or, and that's the good news, you can also use a Kafka operator. Operator, that's a concept which emerged a few years ago in Kubernetes. And an operator pattern in general means that it provides you an option to write code to automate a specific task which is beyond what Kubernetes provides you. So with Kubernetes, you get already stateful sets to manage some kind of state, and you get an option to connect to persistent volumes. So that's all fine. But you need to implement a specific server-side logic, and that's the complex part. Like in a stateful distributed system like Kafka, you have to manage the rebalancing, the version upgrades, the security automation, the automation of handling failover. And that's what then a Kafka operator is for. It's one specific implementation of custom resource definitions. So under the hood, it uses just just Kubernetes standards like Helm charts for provisioning, like config maps, stateful sets. But the magic is in the end the Kafka operations part, which is implemented by the Kafka operators. On the market, you can, for example, get Confluent operator. You can get an open source tool from Banzai Cloud, or also IBM, Red Hat. They also provide a StreamC operator. They all have the different trade-offs and pros and cons, and depending on, do you want to run that 24/7, and do you want to get support and support for the whole platform and all these things. let's take a look at one example at the Confluent operator. So the good news here is that Confluent provides Confluent Cloud, which is our serverless offering on the major clouds, so that you can use Kafka as a service. That's even easier for you. But if you have to manage it by yourself on Kubernetes, then you can leverage the Confluent operator. The benefit here is that we have a lot of experience with operating Kubernetes and Kafka on top of that for a long time already, and really at mission critical scale and availability. Because we also choose to use Kubernetes as our infrastructure for the Confluent platform. The reason for that is that with that we are vendor and platform independent. We can run that in any major cloud without having to change all the things and the integrations under the hood. And therefore we have major experience with running Kafka and Confluent on Kubernetes. And with that we decided to implement Confluent operator, which is already GA and available for production support, including 24/7 support options. And that is really a tool to provision and deploy and manage the Kafka and Confluent platform on any Kubernetes environment. And this includes really the whole Confluent platform, not just the Kafka brokers, but its whole ecosystem. And it really operationals years of experience with running Kafka on Kubernetes. And that's all these hard parts I mentioned before. That's what we are implementing under the hood in a custom resource definition, so that you can just use it to deploy and run Kafka 24/7 in your infrastructure. This includes things like rolling upgrades, like security automation with certificate management, but also monitoring and then sending data to other monitoring tools like Prometheus or Control Center from Confluent. So it's really a tool which helps you reducing the risk and the burden of running Kafka and Confluent on Kubernetes infrastructures. Here's just one example. So it's just standard Kubernetes under the hood. So you use persistent volumes, you use Helm for provisioning or changes, and then it simply provides different pods with Kafka brokers and Zookeeper and other components. It uses config maps, load balancers, and then the orange thing here, that's the magic, that's the custom resource definitions for operating Confluent platform under the hood. You just use a Helm chart to provision that, and then it runs continuously 24/7. And if you want to do an upgrade, you just change the YAML file and it in a declarative way, and then it does the upgrade and all the complex stuff under the hood for you. So with that, if we reconsider the key requirements for microservices with Kafka and Confluent on Kubernetes, you still have the advantages of Kafka, like being decoupled and data aware. But in addition to that, you're now fully elastic with all the features of Kubernetes, like scaling up, scaling down automatically, doing rolling upgrades with the support of the operator toolings. And with that, you're even more flexible than before with just Kafka. So that's really huge. However, one big thing is missing, and that's the operational transparency, which is still not there yet. And also, you're still not that flexible regarding different configuration options for security and routing and so on. This is now where a service mesh comes in. This is a great complementary concept and paradigm compared to Kafka and Kubernetes. It's not competitive, it's complementary. Let's take first a look at the general concept. And here, the first thing we have to understand is the concept of a Kubernetes pod. Especially if you're not a native English speaker, like me in Germany, to me it was never clear what a pod means in Kubernetes. If you know English well, then this means that it's really a small herd of whales or dolphins. And this explains really how this now makes sense. Because one Kubernetes pod, so one deployment component, includes many small pods, right? And in one pod, you then have again different containers. And these abstract the logic from each other. The main deployment mode in Kubernetes is a pod, and this includes different kinds of containers. And this is important to understand because a service mesh more or less leverages the Sidecar Pattern as main feature. This means within one of these Kubernetes pods, you have, for example, one application and then one proxy, which is the sidecar to that, which adds additional logic. And the great thing about this sidecar is that it provides isolation and encapsulation between the different tasks you have to implement. And that helps a lot in a complex microservice architecture to standardize things. So a service mesh, it's really also a microservice pattern, mainly to create more visibility and ease of configuration for the whole ecosystem. For that, it has a data plane The data plane in the end is really the proxy which you add as a sidecar to each independent microservice. And on the other side, you also have a control plane which controls all the different microservice proxies. We will go into much more detail here, but this is the main idea behind the service mesh. And here on the bottom left, you see a few examples of different technologies for that. There's different kind of control planes available like Istio, and different kind of data planes like Linkerd or Envoy, for example. It's also important to see older technologies like HA proxy or Nginx, which are also great sometimes for a proxy. You don't always have to use the cutting edge stuff, and sometimes the older ones are more mature and easier to use and totally fine for specific use cases like load balancing. The important thing here is that the service mesh is an out-of-process architecture. This means that each process is self-contained, and this means that there is no central process running, right? This is the important thing about the proxies, which are sidecars, part of each microservice. And this is also a very important benefit compared to these fat client proxy libraries, which exists for some years, like Finnegal from Twitter or Historic from Netflix. These are used in different ecosystems today. And the disadvantage of these, they are typically built for one language like Java. And also they have to be deployed with each application or microservice. So it's much harder and the burden is bigger for deploying all of the systems in your microservice architecture. With these new service mesh concepts and the technologies like Istio or Linkerd and Envoy, you can really decouple this kind of proxy logic from the application. Instead of using a fat client where you embed the logic from Historic of Finnegal as a library or as a jar file into the application itself. And that's the huge difference why we now talk here about a service mesh really with these new modern technologies. So now with an understanding of service mesh in general, let's now think about the two components of it, the service proxy, which is also known as the data plane, and then about the control plane on the other side. The service proxy is really often just a load balancer, often with more logic, right? So we have to understand that there's two different concepts here, and we are looking here at the OSI model, like either you have a proxy or load balancer at level 3 and 4. This is the first example on top where we really use the TCP protocol to do load balancing. That's level 4, right? On the other side, we also have level 7, which is then application specific, like it's at the bottom. Here we do the load balancing not just on TCP level, but on the higher level 7 application level. Like in this case, we are using HTTP, and based on some header information, we are now using this information to route to backend 1 or to backend 2. All right? And so it's also important to understand, so while I often, or in general, the information on the web about proxies and service mesh is using this level 4 versus level 7, logic, it's not always the right abstraction level. It still some kind of makes sense, but sometimes it's also a question, is this really level 7 or level 4? So it depends a little bit on from what perspective you're looking at that. But it works well to understand the details and more. With that, let's take a look at one example for load balancing in a proxy. And here you see the example of Envoy. Envoy is one open source proxy you can use. And the great thing here is, as you see on the left side, it has different features, both for level 3, level 4 filtering on the one side, but then also many advanced level 7 things like HTTP filtering or routing. And then even advanced support for other technologies like gRPC or even Kafka protocol in the meantime. And also it has additional things like service discovery, health checking, advanced load balancing, that's things like circuit breaking. And so you can do many things with that. The main advantage I see from these kind of proxies is really that you can create observability. That's stats, that's tracing, that's logging, but you can get the whole view of the whole microservice architecture and not just of the independent server or client components. So here you see the service proxy is a sidecar typically here. So you always have the different applications here, circles in different colors. And all of them use the same proxy technology here, which could be something like Envoy. And then you communicate via proxy with other microservices. That's the main idea of the service proxy. Here's an example where the service proxy is the inbound sidecar. So here, one service in purple says, hey, I have a new IP. But the other service says, well, I don't care. So actually it doesn't say to the other microservice because he doesn't care. And the reason is that the proxy in the middle is doing the magical routing or transformation. So only he knows about the IP. The service on the right side doesn't care at all about that. And so only the proxy has to know. Another example where the service proxy is the outbound sidecar. The left service says, hey, I have an error, but no problem. I see an error. He doesn't have the error. He wants to connect to the service on the right. And so he sees an error. And so he says, well, it's okay. I connect to you every millisecond and until you work again. However, the right service typically does not want to get all the traffic because he's down anyway. Or sometimes it would make even things worse. And therefore, the outbound sidecar here says, well, you can try to request, but I don't allow this. So either I only retry every second, or even I use advanced routing patterns here, like the circuit breaker, where you increase like 1 second, 2 seconds, 4 seconds, 8 seconds, and so on to do a service request, right? This is best practice which other services use for a long time already. Like if you have Google Mail and something has bad internet connection, this is a common pattern there. But now you can easily do this with these proxy services and configure it for every microservice you build. Therefore, if you think about the service proxy features, there's a lot of great things in here. It's about getting different metrics and traces and service discovery. You can do very cool routing things and even things like A/B testing, green-blue deployments, often with just one configuration in your JSON or YAML file. And you can do powerful things like protocol translation, like from HTTP to gRPC, both request response, or even migrate it to the Kafka protocol in a streaming way. And then, of course, there are different things for security, like mutual TLS or SSL termination, which you can really configure for each microservice with just one configuration in the end. And it also integrates well with other third-party tools. But the really biggest thing about all of that is that you get observability in your microservice architecture end-to-end, and not just specifically for one dedicated service, but end-to-end in Kafka perspective, producers, brokers, consumers, and even other independent services. And that's the great thing to solve this challenge of the distributed microservice architecture. So here's an example why Lyft has built Envoy and open sourced it afterwards. Their main reason was that developers should be able to spend their time on writing business applications. And therefore they have built exactly these features I mentioned, like supporting different languages with different protocols and creating this kind of observability and decoupling from the systems for different microservices. That's why they have built Envoy and open sourced it. So there's great material on the web, for example, by Matt Klein on YouTube, and you will find slides and articles by him about that. So if you take a look at today, and with today here you see it's from KubeCon 2018. Here Lyft uses the proxies for 100% of communication coverage. And with that you really can get monitoring and debugging and firefighting for your whole microservice architecture. And that's really big because first of all you have the observability, but the second thing is you have the abstraction between the network from the application developers. It's much more transparent and flexible because the application developer just built its microservice technology and business logic and doesn't have to care about the network and the other stuff, which is always configured in the proxies here. Here is another example, and so while I'm focusing a lot on Envoy and Istio in this talk, the main reason is because they have best Kafka support yet, but there's great other technologies like, for example, Linkerd, which in version 2.0 is, for example, what I read from the web, much easier to configure than Istio, for example, right, or than Envoy. So here's just one example to show this one, and here you can see that by changing just one configuration, in this case the routing, you can improve the availability of your system. So you can either do round robin for doing the routing or least loaded, or you can do a much more powerful exponentially weighted moving average. This is just config change, but on the other side for the availability, this makes it much better, as you see here. From 95% with round robin to 99.9% by just one change in how to do the routing differently. And this is the powerful things you can do with these kind of proxies like Linkerd or Istio in a very simple way for your whole microservice architecture. With that understanding about proxies and the tools behind like Envoy or Linkerd, let's now think about the second part, the control plane. So the control plane is the other important part. Even proxies alone are great, right? What I just discussed is there's things on the right. You have the sidecar proxies for the different microservices, and you can deploy one proxy to every sidecar. But then typically, as soon as you get more than 2 or 3 microservices, you want to also automate how to control and configure these different proxies and microservices. And therefore, in the beginning, it might work with using the human control plane, which does this magic of configurations and so on. However, the real goal in a service mesh then is to have also an automated control plane for that. Here you already see a more advanced example, but on the top left, you see the less grumpy human, and he can use a control plane UI, which manages all of that under the hood. So all the left side is more or less the control plane, and on the right side you have the different independent microservices with sidecar proxies. So that's really what you want to have, one control plane where you automate how to set the policies that will be enabled by the data plane. Here is one example of that. This is Istio. Istio is just the control plane. So for the data plane, for the proxies, it uses Envoy under the hood. You can also add other proxies, but by default it uses Envoy, so this is a powerful combination. And Istio is, as I said, the control plane. You see it in the picture here at the bottom side, all these components, and it talks to the different independent microservices. Or better, it talks to its proxies only, and then the proxies talk to the microservice. And here you have the different features, like the pilot is one component which does the service discovery and sends the configuration to the proxies. Then you have the mixer for policy enforcement and gathering the telemetry data for monitoring. And you have more components then for ingress and egress and for security and certificate management. That's different components, and you definitely have to take a deeper look into Istio or into other technologies, and the same is true for the proxy like Envoy, to understand it in all detail. But on a high level, it's really separated into the control plane and into the different proxies which do what the control plane tells them. And also great, so tools like Istio as control plane, they don't implement everything by themselves, but they connect to other different features and systems and frameworks. Like tracing, when you want to find the outliers of all the traces. That's what's not implemented by Istio, that's integrated with other tools like open source tools like Zipkin or Jaeger, or any commercial tool like New Relic or AppDynamics. And for metrics, the same for Prometheus or Datadog. And then for logging, you can also integrate with log analytics tools like Elastic for open source or Splunk for commercial. So that's all what it is, automatic plugins, and you can easily integrate all of that. And this is really then the pillars of observability, having the control plane and embed the different things you want to monitor and manage. So now let's think about Kubernetes as core, right? And Envoy and Istio as one example, or any other proxy like Linkerd or any other control plane. With that, if we take a look at the key requirements for microservices, with that we are very flexible because we can configure everything, decoupled from the business logic. You can configure things like security or routing or monitoring in the proxies and control that from the control plane and its policies. And with that, finally, we have this operational transparency over the whole microservice architecture. This kind of thing is missing, it's not about data awareness, and it's not about decoupling things. So by default, these technologies use HTTP or gRPC. So it's very different from Kafka, and it's not decoupling systems well. On the other side, it's very elastic. So that's also the beauty of service mesh on top of Kubernetes. So this has some great new benefits now, but it's missing the other parts of the puzzle for decoupling and data awareness. And one last point now here is to mention also the service mesh interface. So today there's many technologies and vendors, but this is also getting standardized. And I think for these kind of things, it's a great thing because it standardizes the most common service mesh capabilities like traffic policies, traffic telemetry, and traffic management. So that later in 1 to 3 years, all of these service mesh tools, both for proxy and control plane, will hopefully implement these standards from the service mesh interface, that they can even work together very well, so that you don't have to use the same proxy or control plane technology for your whole microservice architecture, which might get very big over time. So now, after we learned about the advantages on Kafka and its ecosystem in Kubernetes and also service mesh with Kubernetes, now let's think about, well, how to combine them to really get all the key requirements of a microservice architecture together. First of all, and that's also important to understand, in service mesh, when you take a look at the tools and frameworks, they typically talk about request response. This also happened about microservices until a year ago or so. Everybody thought microservice is just HTTP and REST. So this is not true anymore, while often it makes sense, but in the meantime, it doesn't really matter if you do request response or event streams. This is completely independent of the story about building microservice infrastructures. Like with Kafka in the middle, you have a decoupling systems, and it doesn't matter if your clients, like producers or consumers, stream the data or do a request response to it. Both is totally fine and is battle tested and proven and works very well. Right? So in the end, in most architectures in today's world, you need both request response and event streaming. So I don't want to start this kind of FUD about REST versus streaming. Both are great. They have their use cases, and typically you need both of them. However, the big thing really is with Kafka in the middle, you have it event-based, and then you can easily build real-time and scalable streaming applications, but also add request response, RPC, or even batch consumers to the data. The other way around is not possible. If the central system is just request response or doesn't scale well or doesn't support a large throughput, then you cannot build a real-time streaming around that, right? So that's the big difference why with Kafka in the middle, you can start small with small data or even with just request response from the outside, but then later build streaming on top of that with new applications, and you can easily scale up. And that's the reason why so many people use Kafka for microservice architectures, no matter how much you are streaming or doing request response today and in the future. So why not use them together, service mesh and even streaming platforms, right? This is now an idea here. In this picture where we see it on both sides, we have seen before the examples for inbound proxies and outbound proxies. Makes sense on both sides. So here you see on the left side Kafka producers, in the middle the Kafka brokers, and on the right side, the Kafka consumers, right? They all can leverage proxies. It need not be all, right? So some of them, if they don't need a proxy, they don't use one, right? That's what the other great thing about the service mesh and proxies. You can just use it where you need that. Like at Lyft, everywhere, if you want to do that or need that. In some other cases, it might not make sense, or the complexity is too high to edit everywhere. For example, not every application is running on Kubernetes, right? And then it's getting much harder if you have still to integrate with your monolith or with your legacy mainframe. Do you need a proxy in front of that? Maybe, maybe not. So more from Kafka perspective again, this is the domain-driven architecture I showed before. Here you could add the proxies everywhere, as we said. And here now again, the understanding is important. Both the broker side and the different clients could have proxies. And then there could be the control plane, so which defines the policies and sends it to the proxies. In this case, the proxies could be Envoy, the control plane could be something like Istio, or maybe you use just the proxies and no control plane yet and do it manually or with standard Kubernetes tools, for example. There is all the different options you have. Just decide what you need. Often really important in these microservice architectures, however, is that in the Kafka server side is often very separated from the client side, also from the operations teams. And therefore the clients often don't know the ops team and the other way around. And therefore sometimes a proxy helps the one or the other team a lot. For example, if the ops team says, no, we only support TCP, then you would have probably to add a proxy to the client side to migrate your HTTP protocol to TCP. Here's now a few visions about how to use Kafka together with a service mesh. This is actually from Gwen Shapiro. She talked about it mid of 2018 already. There's a great YouTube video with the recording of her talk. So there are different ideas about how you can combine service mesh and Kafka, either from one perspective to hide Kafka or to introduce Kafka. So in this example, you have on the left side your microservice, which is using REST to talk to a service, right? And actually use the proxy here to redirect it to Kafka. So this service doesn't even know that it's speaking with Kafka. It's just speaking REST, and you don't have to change the service. Or maybe from organizational perspective, the other team says, no, it will not change the service. Then you can put the proxy on top of there. And someone else, the purple right here, this service only understands Kafka, so he's only consuming from Kafka. He doesn't care or know that the left service is using HTTP and a proxy there. So that's a great way to hide or introduce Kafka in the middle here. Also, if you think about migration processes, where you could do this step by step to building a more modern and more scalable, robust architecture, where Kafka sits in the middle for some microservices, instead of just doing point-to-point communication between each microservice with HTTP. Another vision is that you could use Kafka as part of the control plane. In this example, Kafka is deployed, right? And then on the left side you have a REST microservice. And then the proxy is still sending it directly to the other microservice, because that one is still a point-to-point connection, because the other service is also using HTTP and you need point-to-point here. On the other side, you could then also use the proxy to send the logging information to Kafka. Kafka is large scale, it processes logs, you can easily integrate it with Elasticsearch or something else, or some tracing tools. And therefore, this is a perfect combination without even the need to change the client side. You'd send the logging data to Kafka, no change to the client. And that's great advantage. On the other side, then in the next step, you could think about, well, I now have on the right side the purple REST microservice, and maybe we could also add logging here and send it to Kafka. Or maybe we could even do a migration here and translate it to TCP and let this service also speak to Kafka, and then really decouple the microservices. Because here you see what I mentioned before all the time. If you don't use Kafka in the middle, these two microservices are coupled to each other. It's point to point. If one service is down, the other one cannot produce data anymore. If Kafka is in the middle, it's the back pressure for these services. And that's great. The third vision is that you could use Kafka as a service mesh. So this simply means that you directly use the proxy of a service and communicate with Kafka as TCP protocol. So that's another great thing. I will cover that in a few minutes in more detail. Today, most of these proxy and control plane technologies do not support the Kafka protocol directly. But this is, of course, also perfect. If you have a Kafka broker deployed and can use Kafka as a service mesh and directly send data from the proxies there in Kafka protocol via TCP. And the fourth idea is that you have a front Kafka more or less as a service. This means that, for example, you use Confluent Cloud, which is serverless for you, right? We provide Kafka as a service with consumption-based pricing. You don't care at all about the broker side, about deployment, operations, fine-tuning, throughput. You just pay as you go for what you're using. And here you could deploy the proxy in front of Kafka so that still the people, the services are separated from each other, and you still don't even care if the outside world is HTTP or gRPC and how that works to each other or what the routing policies are. So that's what you could define as kind of front Kafka as a service. So this is different visions, and Gwen really talks in much more detail about these ideas. So you can also watch her talk about that. But with this understanding about what you could do together with Kafka and service mesh, let's make it now a little bit more specific and with some examples. And think about potential features for Kafka and service mesh implementation. Not everything I show here is there today, but hopefully this will now be implemented. The first part is protocol conversion from something like HTTP and gRPC, which is request response, to the streaming Kafka world. And this is what you could easily implement in a Kafka proxy for many different reasons. To dump it to a Kafka stream for logging, to do protocol parsing and then adding logging and other stats stuff, to shadow requests to Kafka instead of HTTP. You can also integrate it then easily with Kafka Connect and the whole ecosystem of connectors easily without having the hard coding from how to get HTTP stuff into Kafka Connect. Another thing, of course, is the proxy features, like I'm doing dynamic routing and rate limiting, filtering, add compression, or even more fancy stuff like automatic topic name conversion, for example, for Canary releases or blue-green deployments. All of this can then be done on the Kafka protocol level on the TCP layer, right? And that's huge, because what you can do today already with, for example, with HTTP headers, that's things which you could do with Kafka headers or other Kafka protocol information. Monitoring of tracing, of course, monitoring and tracing. Kafka is built for large scale. It's used a lot for log analytics and these things. So things like data lineage, audit logs, and other client-specific metrics and analyzing all that. Here, all of that could be done on the Kafka level. It's more or less layer 7 with Kafka protocol, but TCP under the hood. Security, of course. I mean, you already today can use something like HA Proxy or Envoy or Linkerd to do SSL termination in the proxy before you go to Kafka or mutual TLS. But you can even do more advanced stuff if you directly can access the Kafka layer on top of that. Or then things like validation of events for message schema, headers, and so on. So there's a lot of cool things. Some of them you can already do today, at least on layer 4, right? On TCP level, but not specifically with Kafka input or structure or protocol. But this is now coming more and more. On the other side, after I've talked a lot about the great advantages of service mesh and how to combine it with Kafka, I also want to make the point that there is always a trade-off between the benefits and the cost of doing logic outside of Kafka and making the deployment operations as simple as possible. So just to give a few examples, the community now will replace Zookeeper with part of the Kafka broker implementation, so that you don't have to run Zookeeper anymore, which makes operations much harder. And this is now learned after many years of operating Kafka, that running an additional component is often a harder thing. And the same might be true for you running additional proxies in addition to the Kafka broker, because then you have a separation of concerns and configuration. Often it's a great thing, right? But sometimes it makes it even more complex. So it's always the trade-off between benefits and cost. Another example is that in Confluent we are now also introducing things like server-side schema validation. We by intention do that on the Kafka broker to do it close to the broker, again from operations perspective and so and about scaling one component versus different ones. This is the simpler choice here. Or other things like tiered storage for auto-scaling. The thing is, how many different components do you want to have in your infrastructure if it has to run 24/7 and be elastic and scalable? Is it better to have more or less of these components? And there is no one correct answer. It's always a trade-off. And therefore, some things might be better for your use case inside the Kafka ecosystem, and some things might be better outside the Kafka ecosystem in a proxy. So it's always a question of what you want to do and the benefits versus the cost. With that, let's now really take a look at some specific use cases for service mesh implementations with Kafka and the service mesh tools. We already have some examples where you can take a look in more detail. So what can you do? I mean, really, it doesn't really matter what kind of service mesh implementation you choose, and if you just want to use a data plane or proxy, or combine it with a control plane. What you can already do today, and that's even true with things like HA Proxy with the classical load balancer, is level 4 filtering on the Kafka client or on the Kafka broker. So here HA Proxy or Nginx is the proxy for you, right, of the service mesh. And here you already can do all of the routing they provide, like rate limiting or configuring mutual TLS. That's things which are possible today without any problems, and many people are doing that already. On the other side, you can also do much more level 7 things already, which is more Kafka-specific application logic. Like putting a REST proxy in front of Kafka brokers to do HTTP communication to Kafka. Like using Envoy's Kafka protocol filter to do really specific Kafka implementation. Or you could implement your own custom project. Here's an example of Travis Jeffrey, and he has built a Kafka proxy by himself. Let's take a look into some of these examples in more detail. The first one is on level 4, right? Let's keep it simple first. So here's an example of how Kafka and Istio are used together at Banzai Cloud. And that's a pretty impressive example. You can also Google for that or take a look at the link below in the blog post. What they are doing, they are running Kafka together with Istio, so that they use Istio and the service mesh to do SSL configuration in a proxy outside of the Kafka brokers. And the very interesting thing here, you see this in the measurements, is that that if they compare the combination of Kafka and Istio together, there's not even a performance trade-off by using the proxy for mutual TLS configuration. You even see that with Kafka and SSL TLS, it has on Google 274 megabytes throughput per second. And if you actually use Istio for mutual TLS, you even have a bigger performance with 323 megabyte per second. So that's pretty interesting. And they describe in much more detail how they run a service mesh together with Kafka. The important thing here is this is level 4, right? And therefore it's clear to have this clarification of what you do. This is what you also can do with an HA proxy, for example, already. It's just filtering on the TCP level, not related to Kafka specific logic or Kafka headers also. Here's an example of their architecture. They even run it over different Kubernetes cluster, and here you see each Kafka broker has an Istio sidecar, and each zookeeper has one, and then also the different services have one. The services here are, in this case, the microservices, which are doing the performance management. So these are, from Kafka perspective, these are the client tools which are running. So this is a pretty interesting architecture to understand how you could use a stateful infrastructure like Kafka and zookeeper together with clients to build highly scalable and high volume in such an application. Another example now on level 7, if we want to use Kafka together with our services, here we see now if we have a microservice on the left side which only speaks REST and HTTP, you could put an Envoy proxy here, and either you just use HTTP, both for the point-to-point to the other REST service, right? But also you use HTTP to speak to a Confluent REST proxy, because in this case you don't want to transform it to TCP, or the technology under the hood does not provide it, and therefore in this way you can easily also speak to Confluent via HTTP in this case, because Kafka itself, it's only TCP, right? On the other side, and that's great news, so there is actually Kafka support in Envoy already. The pull request was finally merged in May 2019, and so today Kafka is supported by Envoy on level 7, like MongoDB and some others, so you can do much more fancy stuff than just doing the TCP filtering. Now you can do Kafka-specific logic for filtering or for security or for other rules. Of course, now you can and have to implement more features, so it's not finished there yet, but this is the key merge which was needed, so that now Envoy also supports the Kafka protocol filter. So this is level 7, but using TCP. So in Istio, however, this is not supported yet, because now first there was the Envoy pull request, and now after that, now the Istio people can implement logic in Istio for that, right? So the TLDR here is that level 4 already works in Istio, of course, because it's just the normal load balancing stuff, but level 7 needs some more PRs here in the Istio project. But you already can use all of them together, but today still with some limitations regarding level 7. But in Banzai Cloud, you just saw an example how you can still combine them already. Or you try out, for example, if you just want to use Envoy, this great new pull request for the Kafka protocol. So then when you have this kind of pull request in Envoy, then it's great, because then the client still speaks REST, and you're still speaking REST to the other microservice directly. But then now you can also speak directly with the Kafka broker in the Kafka protocol via TCP, because this is the pull request I just mentioned for Envoy, which is there now, right? And this makes this, of course, much more powerful. And now this is open to implement many great new specific Kafka-related rules on top of Envoy proxy for that. And this really makes the service mesh then much more powerful also for Kafka use cases. So with that, if we now think about the key requirements again for microservices, if we run Kafka on Kubernetes and leverage a service mesh like Envoy and Istio, then you have everything. Kafka decouples the system. It also creates the data awareness and processing. And that in combination with Kubernetes and the service mesh creates high flexibility. It's also operationally transparent and elastic. And that's the final goal we want to have, right? So microservices are not a free lunch, but you can get there, and now with a lot of great tool support for that. So in the end, the summary is even streaming platforms and service mesh, it's really a match made in heaven. So they fit together very well. We see all of them have their own use cases, and you can complement them to each other to solve the problems for building a really highly scalable microservice architecture for high throughput, for decoupling systems, and for providing support for both streaming and RPC and request response. So with that, let's come to the takeaways, which I mentioned in the beginning. So Apache Kafka really decouples the different systems, and not just including event streams, but also other communication paradigms like request response. Kubernetes provides the cloud-native infrastructure you need for the Kafka ecosystem. You have learned about the Kafka operators, which provision and automate and manage Kafka in the ecosystem for you on Kubernetes. And you also learned that more or less Kubernetes is the way to go today. And then on top of that, the service mesh really helps, especially with things I think like security and observability. And the big thing is really also at ecosystem or organizational scale. So this is orthogonal to the goals of Kafka because it's bigger. It's more about the microservice architecture and not just the Kafka and the broker side and the clients, right? So it's very complementary, and it also in the meantime supports Kafka itself, either just on level 4 depending on the tool you use, or for example with Envoy you can even leverage TCP and Kafka protocol together with the service mesh technologies. And I think that's really great. And with these lessons learned, thanks for watching. Please contact me on LinkedIn if you want to stay in contact, or drop me a Twitter or email if you have any questions or any feedback. Thanks for watching. Ist das wieder nicht da? Das kann doch jetzt sein.